Everybody. So today I'm going to continue and conclude talking about radical reactions. And I do remind you that tomorrow we have the quiz at 9:50 to 11 a.m. like usual, but remember there is no lecture because the building where I'm giving these lectures will be closed and I can't give a lecture from home. I sent a message to the class to remind you about that, so I hope everyone is aware. Okay, so last time I want to revisit a problem that we were working on last time, dealing with the prediction of the percent yield of radical products from selectivity factor and statistical factor. So I want to do another problem of that type because maybe one a little bit more complicated than we did last time. So it's this calculating percent yield of radical halogenation. We did a problem like this last time. I just want to do another one. All right, and so the data that we need here are the selectivity factors for abstraction of a primary hydrogen, a secondary hydrogen, and a tertiary hydrogen by chlorine and bromine. And so these numbers actually move around based on the temperature of the reaction and also whether the reaction is photochemical or thermal, right? And so I think this is the data set that I gave you last time. These are the reactivity factors or the selectivity factors. Okay, so let's try this out again. So I'm taking this guy and I'm going to react him with molecular halogen. This could be Cl2 or Br2. And the data set that I've presented here is for 150 degrees. Okay, so I want to start off right away with a question. How many radical bromination products am I going to get? I'm excluding stereoisomers. Just how many different products am I going to get? So tell me in the chat. So how many different products am I going to get? How many different constitutional isomers of halogenation am I going to get? So tell me in the chat, how many products? Anybody have a guess out there? One, no, more than that. Well, one major product, but let's say how many products total possible, right? Both major and minor. I guess the most popular wrong answer is 5. Okay, how about 4 different constitutional isomers? Okay, so the halogen is replacing a hydrogen, right? That's what happens in a radical reaction. The halogen is replacing the hydrogen, and I see that there are 4 types of hydrogen here. You know, the answer to the question, how many radical halogenation products, is the very same as the answer to the question, how many NMR signals? Because halogen is replacing hydrogen. And chemically equivalent hydrogens will lead to indistinguishable products. So if I were to ask you how many NMR signals am I going to get from this, I hope you would say 4 and not 5, because these two methyl groups are equivalent by a rapid mechanism. This bond rotates, and this methyl group turns into that one, and that methyl group turns into that one. The 3 hydrogens of a methyl group are equivalent to each other, and these 2 methyl groups are equivalent to each other by a rapid mechanism. Okay, so there are 4 products. I could replace one of the hydrogens in that methyl group at 8 o'clock, but replacement of a hydrogen on that methyl group at 12 o'clock is going to give me the very same constitution. So that's 1. And then I could replace the hydrogen down here at this tertiary center. And then I could replace a hydrogen over here at this secondary center. And then I could replace a hydrogen at this methyl group over here. But this methyl group on the right is not equivalent to the methyl groups on the at 8 o'clock or at 12 o'clock, so that's a different product. So there are 4 possible constitutional isomers. And if you're very observant, maybe you notice that this guy here has a chirality center. So this is actually going to come out in R and S flavors. This guy here has a chirality center. So this is going to come out in R and S flavors as well. But those are stereoisomers. We're just talking about constitutional isomers. Okay, so now for the numerology for chlorine would be, okay, we have this is replacement of a primary hydrogen. So the reactivity factor is a 1, but there are 6 equivalent hydrogens on those 2 methyl groups that will lead to the same constitution. So there's a statistical factor, and that is 6. So 1 times 6 is 6. Okay, so now here, this is replacement of a tertiary hydrogen led to this product. So for chlorine, the reactivity factor is 7.2, and there's only 1 such tertiary hydrogen, so that's the statistical factor is 1. Okay, this guy over here, he's secondary, so the reactivity factor is 4.4, and there are 2 such hydrogens, so the statistical factor is 2, and then this is a replacement of a primary hydrogen led to this last product, so the reactivity factor is a 1, and the statistical factor, since there were 3 hydrogens that could be replaced, that's going to be a 3, leading to 3. Okay, so the sum for the chlorine, 6 plus 7.2 plus 8.8 plus 3, that's 25. The sum for the chlorine numbers is 25. And so we're ready to calculate the percentage of each product. So this is going to be 6 divided by 25, that's 24%. This is 7.2 divided by 25, that's going to be 29%. Okay, so this is 8.8 divided by 25, that's 35%. And this is 3 divided by 25, that is 12%. Okay, so one of the things that we've been saying about chlorination all along is that it's unselective, because that first propagation step, regardless of whether it's a primary, secondary, or tertiary radical that is involved, is small, according to the Hammond postulate. So chlorine doesn't care about radical stability. And if you look at these numbers, the reaction is a disgrace. right? Because we are going to get pretty major amounts of a lot of stuff. And when we run a reaction in the laboratory, we want 100% yield of one thing, not major amounts of 4 different things. Okay, so now let's do the very same calculation with bromine. So this is going to be primary selectivity factor of 1, statistical factor of 6. This is going to be tertiary. Oh, that's a whopping big selectivity factor of 1700. And then the statistical factor is 1. Okay, so this guy is secondary. The selectivity factor is 80. And there's 2 of those for 160. And here we have another primary, replacement of another primary. So selectivity factor is 1. And the statistical factor is 3, leading to 3. Okay, so the sum, just ran out of room here. The sum was 1869, which was a very good year for the Austro-Hungarian Empire. And so now dividing up these numbers to get the percentages, we see that for this guy, even though there are 6 hydrogens that could be replaced because we're producing a primary radical and because bromination is selective, it would prefer to form the product that results from the removal of the hydrogen atom that leads to the most stable radical. We get less than 1% yield of this guy. This guy is a whopping big 91% for the replacement of the tertiary. This guy is 8%, and this guy is less than 1%. So this reaction, although it didn't give us 100% yield of one product, it's still, the numerology worked out well enough that this is going to be a useful reaction. We're getting more than 10 times of something than we get of the something else, and vanishingly small amounts of these other things as well. Okay, so we did a problem like that last time. I just wanted to do another one, maybe a little bit more complicated than the one we did before. Okay, so now we're going to introduce 2 new reactions. One of them will not be new to you if you're taking the lab, but not everyone is taking the lab. And that is allylic and benzylic. Is it a Y? I think so. Benzylic bromination with NBS, N-bromosuccinimide. So N-bromosuccinimide is a reagent for allylic and benzylic bromination. So what do these vocabulary words mean? An allylic hydrogen is a hydrogen that is not bonded to a double bond, but it's bonded to a carbon that is bonded to a double bond. So for example, something like this, that is a benzylic carbon, and this would be, sorry, this is an allylic carbon, and this is an allylic hydrogen. So the allylic carbon is not part of a carbon-carbon double bond, but it's directly bonded to a carbon-carbon double bond. An allylic hydrogen is a hydrogen that is not bonded to a double bond carbon, but it is bonded to a carbon that is directly bonded to a double bond carbon. So that's an allylic position. All right, a benzylic position is analogous. except that now I've replaced the carbon-carbon double bond with a benzene ring. All right, and this is a benzylic carbon. It's not part of a benzene ring, but it's directly bonded to a benzene ring. And this is a benzylic hydrogen. It's not bonded to a carbon that is part of a benzene ring, but it's bonded to a carbon that is directly bonded to a benzene ring. So this is the vocabulary here. And so we need to recognize what an allylic position is and what a benzylic position is. Anyway, NBS, N-bromosuccinimide, is a reagent for allylic and benzylic bromination. So for example, we would get this guy that has an allylic hydrogen, react him with NBS. We need heat or light. And what NBS does is replaces the allylic hydrogen with bromine. All right, we would have a benzylic substrate, and we use NBS, and NBS replaces a benzylic hydrogen with bromine. So that's what this reaction does, replace allylic and benzylic hydrogens with bromine. Okay, so before we talk about the mechanism or how this reaction works or anything, let's try some product prediction. NBS, heat. Draw the structure of the product. Okay, tell me in the chat what you're going to get. Maybe if you know about the nomenclature, maybe you can type the name of the molecule, right? What does NBS do? Replaces allylic and benzylic hydrogens with bromine. So what would be the structure of the product? Where am I going to put BR? If you can't cook up the name, where am I going to put BR? 1 o'clock, 2 o'clock, 3 o'clock, rock. 4 o'clock, 5 o'clock, 6 o'clock, rock. No? Okay, time's up. So this is an allylic position. There's an allylic hydrogen, right? It's and so NBS replaces a benzylic and allylic hydrogen with bromine. So that would be the structure of the product there. Okay, let's try again. How about NBS and heat? Where am I going to put the BR? Any guesses out there? Tell me in the chat. Yeah, I'm going to put it at 6 o'clock on the ring on the right, right? Because here's a benzylic position, right? This is also a benzylic position up here at 12 o'clock, but there are no hydrogens there. So NBS doesn't do anything to that benzylic position up there. So the product that I would get here would be the replacement of a benzylic hydrogen with bromine. Okay, so that's what NBS does. Now, the mechanism of the reaction is frightfully complicated. Some of you who are taking the lab, but not everyone is, had a lab experience with NBS, but in that case, you used a radical initiator, that benzoyl peroxide. So we don't always have to use a radical initiator. So what I'm going to show you is the mechanism for the reaction in the absence of a radical initiator. The initiator isn't really required. Now I'm going to go through this mostly for the record. What I want you really to focus on with NBS is product prediction, right? Because a lot of these steps of this mechanism are stuff that we haven't covered yet, but I just want to show you this for the record. Okay, the NBS mechanism. All right, so again, just like with every radical reaction, we have 4 stages. We have initiation, propagation, and termination. So the initiation step, N-bromosuccinimide. So this is the N-bromosuccinimide, NBS. And remember last time we said that bonds that involve carbon and hydrogen are stronger than bonds that don't involve carbon and hydrogen. And what happens in initiation is the weakest bond breaks. So I'm looking at NBS and I see that nitrogen-bromine bond doesn't involve carbon, it doesn't involve hydrogen. So this is going to be the bond that breaks fastest, and it breaks home. Oh shoot! No, I thought I'd made a mistake, but I didn't. It breaks homolytically to produce this bromosuccinimide radical and Br dot. So again, I don't like these fishhook arrows, but let's just maybe they help some people understand. This bond breaks, one of these atoms gets 1 electron and the other atom gets the other electron. Okay, it would be nice if that were it, but it's not by a long shot. Okay, so now we also have some allylic or benzylic substrate, right? I'm going to show this mechanism with an allylic substrate. And so this guy reacts with this Br dot, right? We're still talking about initiation. And we get the Br dot abstracts an allylic hydrogen from the allylic substrate. And if this were a benzylic substrate, we would have a comparable and analogous step. Okay, not done by a long shot. Still talking about initiation. All right, so remember that the initiation step doesn't have, that 100% of the NBS molecules do not participate in these initiation steps. Only a very few of them do. So you have tons of NBS left. All of the NBS wasn't killed off in this first initiation step. Initiation happens just a very few molecules. Okay, so now this NBS reacts with the HBr that was produced in the earlier reaction, the earlier initiation step, and whoa, almost missed. And we get protonation. As I said, we're not in a position to fully understand a lot of these steps, but I do want to present this mechanism just for the record. And so we get protonation of one of those, I guess it would be called an imide carbonyl carbons to give you this. Okay, and now finally, fourth and final initiation step is that this guy this protonated carbonyl reacts with the Br minus that was just produced in the earlier step. And these electrons are going to remove this bromine. And we get this sequence of steps to give us this bromine molecule. Okay, so the point of these initiation steps, I know this is complicated. The point of this initiation step is that it has produced an allylic radical and Br2. Okay, now we're ready to get into the propagation steps, which are mercifully short. Propagation, there's the allylic radical that was produced in initiation. That's our chain carrying radical. That's the radical that makes this reaction self-sustaining. We'll see in the second propagation step that we get more allylic radical, so that the initiation step only has to happen a few times. So this guy plus Br2, let me write it this way. All right, so this allylic radical unteams this bromine-bromine bond. The allylic radical is seeking to complete its octet. It does so by destroying this molecule of bromine that was created in the initiation step. And so there's our product. There's the product of allylic, there's the product, that of allylic bromination. Remember how we said that the propagation steps add up to the overall reaction? So now we can write the second propagation step, where we have the allylic substrate, right? There's tons of this left. Initiation only happens a few times. Not every molecule of allylic substrate is converted to that radical. And this guy is going to react with the Br dot that we got from propagation step number 1. And so now the Br dot is hoping to complete its octet. And so it unteams this bond, fishhook arrows here, and we get more chain-carrying, self-sustaining allylic radical that's going to feed into the first propagation step, and the other product of this reaction would be HBr. Okay, so that's the complicated mechanism of NBS in the absence of the radical initiator. Okay, and then we have termination steps, and so I'll just let you work what those are out on your own. Remember, termination steps, any radicals involved in propagation get their dots together to form a new bond between. So we won't deal with termination for this. Okay. So as I said before, what I really want you to concentrate on when it comes to NBS is product prediction, right? And turns out that there are some complications and some limitations involved with the use of NBS. So I want to talk about that now. Is that we have a limitations on the use of NBS. Right, and that limitation arises because the propagation steps involves a resonance stabilized radical. And that causes no ends of problem. believe it or not, right? Let's go back to these propagation steps. See this guy here? The chain carrying, self-sustaining radical. Yeah, that's resonance stabilized. I'm going to be able to move that dot around. And the problem is that now, because the actual structure of a molecule is a composite of all of its resonance structures, I'm going to end up with a diversity of products. I'm going to end up with more than one allylic or benzylic bromination product. Okay. So if I look at this guy here, and react him with NBS. All right, so that's an allylic a position up here at 12 o'clock. That's an allylic position down here at 6 o'clock. It would be nice if the 12 o'clock proton and the 6 o'clock proton were replaced by a BR, but that's not all that's going to happen. A whole lot of other stuff happens. So if we, without writing out all of that mechanism again, we know that we're going to get one of the chain carrying intermediate is going to be this radical here, right, where the allylic hydrogen has been removed in that first propagation step. I'm also going to get another radical where the dot is going to be at 6 o'clock, but I can ignore that because the radical dot at 6 o'clock is simply the pancake flip of this one, right? There are cases where I can't ignore that. Okay, so this is the radical that is formed in the propagation step, but now this radical has a resonance structure in which I can move the double bond up here and put the radical dot there. See, this is an allylic radical, this is an allylic radical, but the actual structure of the radical is a composite of its two resonance structures. And so what NBS is going to do is going to put BR everywhere you see a dot in the resonance structures of this intermediate. So this guy is going to give this product, which is, I guess, what we were expecting, right? Where just the allylic hydrogen has been replaced by a BR. But because the actual structure of the molecule is a composite of its two resonance structures, we're also going to get a second product, right? And that's not good news, right? When we go into the laboratory, we don't want two different products. We only want one. But just NBS doesn't work that way. So we've gotten two constitutional isomers because of the involvement of that resonance stabilized allylic radical. We could move the dot around and we got a bunch of different, we got two different products. Okay, so let's try this again. Let's try this again, a more complicated situation. Just to show you how disgraceful some of these reactions can be. NBS, draw the structure of the products, right? There are ways of predicting what the major product will be. That's graduate school, right? So what I'm looking for here is just draw all of the products. Okay, well, this is an allylic position over here at 6 o'clock. This is an allylic position over here, allylic position at 8 o'clock, I mean. There's an allylic position at 4 o'clock. There's an allylic position up here at 2 o'clock on this ring. And so everything is, we're going to have to put a dot everywhere, and then we're going to have to consider the resonance structures of moving around that dot, and then we're going to quench the dot everywhere we see it in a resonance structure with BR. So this is going to be a mess. Okay, so First thing is, let's put the allylic dot there. We have a resonance structure in which we can move the dot to there, and everywhere we see a dot, we're going to put a BR. So this guy is going to give this product, and this guy is going to give that product. Well, maybe are you thinking that the major product here might be this tertiary center? It would. Okay, so now, but we have more, whoa. We have more allylic positions, right? We have another allylic position over here. Put a dot there, and we can write a resonance structure for that radical where we're moving the dot and moving the double bond to there. And now everywhere we have a dot, we're going to quench that with BR. Wow, this has gotten totally out of hand. Okay, so here are more NBS products, right? Different from the two that we wrote before. And we're not done yet because this guy kind of ran out of room. Let's do it this way. Is going to have yet another allylic position up here at 2 o'clock. And that has a resonance structure in which we move the dot around to there. And now everywhere we see a dot, we're going to quench the dot with a BR. So we got this. Have we seen him before anywhere? Doesn't look like it. So that's yet another product. And we're going to quench this dot over here as well to give that. Have we seen him anywhere before? No, I don't think so. So we get a total of 1, 2, 3, 4, 5, 6 products, right? Reaction's a total disgrace. So the substrate for NBS, if the reaction is to be useful, has to be very carefully chosen, or else you're going to get a huge diversity of products that render the reaction not really useful. Okay, so before we leave this, let's talk about the very same situation with a benzylic position. And that is that, that the NBS works much better with benzylic substrates. And that's because, well, let's explain why that is. So if we were to use the very same logic that we just saw for the allylic position, with the benzylic position, we would say, okay, so this guy, the benzylic radical that is going to form is going to be this one. And now I can write all kinds of resonance structures where I'm moving that dot around, right? So I could write, that would be a resonance structure, and then can move that dot around another way, put the double bond there, put the dot there, double bond here, etc., right? More resonance structures. However, NBS with a benzylic substrate works better because those radical resonance structures in which the benzene ring has been destroyed are not contributors to any great extent to the resonance hybrid in this reaction. So that all of these guys here, all of these resonance structures here are not, they're there. They're just simply not important because the very stable benzene ring has been destroyed. Did you know that benzene is a very thermodynamically stable system? So that these resonance structures that involve the destruction of the benzene ring, benzene's is a 6-membered ring with alternating double and single bonds. That's not benzene. It doesn't have alternating double and single bonds. This isn't benzene. It doesn't have alternating double and single bonds arranged in this ring. So although these resonance structures are there, they appear not to be that important because we don't get NBS bromination products anywhere here on this ring. Furthermore, all of the reactions we're talking about when it comes to radicals are replacement of hydrogens on sp3 hybridized carbon. So the replacement of the hydrogen that lives here at 2 o'clock, that's not an sp3 hybridized carbon. So that doesn't happen. So in this case, really the only product that we see here would be the product of benzylic bromination, which would be that. Right? That's the only product. So there are complications with NBS and with allylic substrates because all of those resonance forms are contributors to the resonance hybrid, but we don't have the same effect with the benzylic position. Okay. So that's the NBS story. Final radical reaction, and then after my break, after I finish this up, I'm going to take my customary break, and then we'll start a new family of reactions. Okay, last radical reaction to talk about is radical hydrobromination. Okay, the overall reaction here, will be an alkene I'm going to write this in words and then just give you some examples, plus HBr, and this reaction doesn't work with HCl or HF or HI, so don't be making up your own reactions. It's an alkene plus HBr. There is a radical initiator here, a peroxide, right? This guy here, this is called a peroxide. For those of you who are taking the lab, you saw benzoyl peroxide, so going to talk about that. The product here is a bromoalkane with bromine on the less substituted carbon of what used to be the alkene of what was the alkene. Okay, wrote this all out in words, give you some structures in a second, and then the inorganic product of the reaction we don't care about is HBr. Okay, so again, before we talk about the mechanism, we don't need to know anything about the mechanism to do product prediction, right? So something like this, plus HBr, plus a peroxide. So I'm going to use benzoyl peroxide. The important thing here is that oxygen-oxygen bond, right? That's what defines the peroxide. And so what would be the product here of this radical reaction? Well, we're going to get bromine. The double bond is going to get knocked out. It's going to be degraded to a single bond, and we're going to get Br on the less substituted carbon of what used to be the alkene. So this carbon, he's tertiary because he's bonded to 3 other carbons. This carbon down here, he's secondary because he's bonded to 2 other carbons. So the product of this reaction is going to be the double bond gets knocked out, it gets degraded to a single bond, and Br ends up on the less substituted carbon, right? And on the more substituted carbon, we have a new H that wasn't there before. And then the inorganic junk we don't care about would be HBr. So double bond gets knocked out. It's degraded to a single bond. Br ends up on the less substituted carbon. And H, a new H that wasn't there before, ends up on the more substituted carbon. All right, so let's do a product prediction. This guy, HBr, peroxides, heat, draw the structure of the major product. Well, it's not only the major product, it's really the only thing that happens here. So where am I putting Br? Tell me in the chat. Where am I putting Br? I'm putting Br on the bottom of the left ring. Exactly. 6 o'clock on the left-hand side. So the double bond is degraded to a single bond, and I put Br on the less substituted carbon. Okay, so now we want to understand why the Br ends up where it does. And so to do that, we need to talk about the mechanism. And again, we're going to have initiation, propagation, and termination steps. The initiation step. We've said many times that bonds that involve carbon and hydrogen are stronger than bonds that don't involve carbon and hydrogen. So in the initiation step, if we look at our system here, we see, well, everything in the alkene has carbon and hydrogen in its bonds. HBr, that's a bond to hydrogen, that's pretty strong. Benzoyl peroxide, the radical initiator, has a weak oxygen-oxygen bond. So it's no surprise, this bond here, he's worth 146 kilojoules per mole. That's the weakest bond in our system. And typically what we see in initiation is the homolytic bond breaking of the weakest bond. So that snaps. We get these 2, I think these are called peroxy radicals, right? One electron went to one oxygen atom, the other electron went to the other oxygen atom. Okay, and so now there's a second initiation step where that peroxy radical now reacts with HBr. There's a ton of HBr at the beginning of the reaction, and this oxygen atom is going to complete its octet by destroying the HBr bond homolytically. We get an alcohol plus Br dot. Whoa, not 2 dots. Plus Br dot. And that's our initiator. This is our initiator radical that now feeds into propagation. And again, do I need to remind you this happens very few times because the reaction is self-sustaining chain reaction? We're ready for the propagation steps. and we're ready to explain why bromine ends up where it does. Okay, in the propagation step, first propagation step, Br dot, this radical formed in initiation, it reacts, it is seeking to complete its octet, and it does so by unteaming this pi bond of the alkene. And so we get this species. But another thing that could happen here is that Br could unteam this double bond in another way. And that would be, let's see, try to draw this in a way that makes visual sense. Like that. So what's happened here is that double bond, that the pi bond of the double bond has been degraded to a single bond. And at one end of where the double bond used to be, we have Br. And on the other end of where the double bond used to be, we have a radical center. So we look at these two radicals and what do we see? Oh, this guy is a secondary radical. This guy is a primary radical. The formation of the secondary radical is faster than the formation of the primary radical because the secondary radical is more stable. And if we were to do all of the numerology for this reaction and draw out the energy diagram and everything like that, we would see that this would be indeed the case. So that this happens and this guy, no good. Okay, so now this is propagation step number 1. Can finish up the reaction now with propagation step number 2, where the secondary radical that put Br on the less substituted carbon is now going to react with HBr. And this radical completes its octet by destroying this HBr bond. And we have bromine on the less substituted carbon of what used to be the alkene. We have hydrogen on the more substituted carbon of what used to be the alkene. That's our final product. And we've created more chain-carrying, self-sustaining Br dot that's going to feed into the first propagation step. Okay, so this is the another way of putting Br on stuff, but this is from an alkene. Okay, so that's the end of the radical story. Now I'm going to take my 10-minute break, and then we will return with a new family of reactions. Hi, everybody, we're back. Okay, so going to start up a new family of reactions. We just talked about one way in which alkenes can react by a radical mechanism, and now we're going to continue to talk about other reactions of alkenes. But before we do that, we have to introduce some important vocabulary, and that is we'll be talking a lot about nucleophiles and electrophiles. So this is important vocabulary, and it's important to recognize what is and what is not a nucleophile and what is and what is not an electrophile. So a nucleophile, this is an electron-rich species that has an electron pair available for bond formation. So some concrete examples of nucleophiles would be something like, for example, the hydroxide ion. The hydroxide ion is electron rich. It's so electron rich that it has a negative charge on it. So that's a nucleophile. And it also has all of these unshared electron pairs that it can use to form bonds to something else. So that would be a concrete example of a nucleophile. Another concrete example of a nucleophile could be the cyanide ion, right? The cyanide carbon is so electron rich that it has a negative charge on it, and that carbon atom has an electron pair on it, which it can use to form a bond to something else. Another example of a nucleophile could be fluoride, chloride, bromide, or iodide. Right, that's also a nucleophile. It has a negative charge. It has electron pairs that it can use to make bonds to something else. Many nucleophiles are negatively charged, but not all nucleophiles are negative. There are some neutral nucleophiles as well, and there can never be a positively charged nucleophile, because in the definition of a nucleophile, the species has to be electron rich. So something that has a positive charge on it can't be a nucleophile. Many are negative, but some are neutral. So a very important example of a neutral nucleophile would be the water molecule. Right, it doesn't have a negative charge on it, but it's still a nucleophile because that oxygen atom has an electron pair available for bond formation, and that oxygen atom is electron rich. It has these unshared pairs of electrons on it. So that's a neutral nucleophile. Nucleophiles can be negative, they can be neutral, but they can never be positive. Another example of a neutral nucleophile would be ammonia or any kind of amine. Once again, that nitrogen atom has an electron pair that it can use to form a bond to something else, and that nitrogen atom is nucleophilic. Another example of a nucleophile, which is much more germane to what we're talking about now, is the carbon-carbon double bond is a nucleophile. Well, of course it is, because in that tiny space between two carbon atoms, you have twice the electron density that you have in a single bond. So a double bond is a nucleophile. What about three double bonds all stuck together inside a benzene ring? Oh, benzene is also a nucleophile. In that tiny space between two carbon atoms, you have double bonds, and you have twice the electron density that you have in a single bond. That's electron rich, and the carbon atoms here have an electron pair. It is shared in this case. In the case of the alkene, that electron pair is also a shared electron pair, not an unshared pair, as we saw in this first row, but benzene's also a nucleophile. The counter image of the nucleophile is the electrophile. The electrophile is an electron-poor species. Many electrophiles are positively charged. That's how electron-poor they are. But some electrophiles are neutral, but there are no negatively charged electrophiles because something that is negatively charged would not be electron poor. So we've already met an electrophilic species, but we never used that word before. A radical is an electrophile. Is it electron poor? Oh my heavens, yes. It only has a septet of valence electrons, right? It wants an octet. It's electron deficient. It's missing an electron. A radical is an electrophile, but it happens to be neutral. We have some positively charged electrophiles as well. And so the positively charged electrophile par excellence that we're going to be talking a lot about is the carbocation. This is called the carbocation. And it's even more electron deficient than a radical because a carbocation only has a sextet of valence electrons. So both of these species are very high energy, they're very reactive, they're very electron deficient. You cannot buy a bottle of radical and you cannot buy a bottle of carbocation at Chemicals R Us. These species have lifetimes on the microsecond time scale at room temperature because most atoms want to have an octet. These guys don't, so that's what makes them reactive. Another electrophile that we're going to be seeing quite a bit of will be, and this is a little bit more subtle, what if we have a carbon atom that is bonded to a highly electronegative atom, such as halogen? Well, this is also an electrophile because the halogen is sucking electrons away from the carbon, so that to communicate that fact, we could put a partial negative charge on the halogen and a partial positive charge on the carbon. And so the carbon in these kinds of haloalkanes, that is considered an electrophile as well. It's electron poor. It's had its electron density sucked away from it by that electronegative halogen. And an electrophile that is very germane to what we're about to talk about would be a hydrogen halide, right? This could be HF, HCl, HBr, or HI. And once again, the electronegativity of the halide is much higher than the electronegativity of hydrogen. So the hydrogen halide bond is polarized away from hydrogen and toward the halogen. The hydrogen end of HF, HCl, HBr, HI, whatever, is an electrophile. Okay, so what we're about to talk about this new family of reactions, which will be the reactions of the alkene. We'll make extensive use of these terms, nucleophile and electrophile. Okay, first up, hydrohalogenation. Hydrohalogenation. Okay, and remember, we're not talking about radicals anymore, right? We just talked about hydrobromination, but that was a radical reaction. So we're not talking about radical reactions. We're into a new family of reactions. And the overall reaction here will be, you have an alkene, you react that with a hydrogen halide, right? So this could be HF, but it never is. HF, HCl, HBr, or HI, no peroxides when we use HBr, right? Peroxides aren't there, so we're not talking about radicals anymore. And what is going to happen here is that the carbon-carbon double bond is degraded to a single bond, and the atoms of hydrogen halide add across where the double bond used to be. Okay, so that double bond gets knocked out, and we're going to get halogen where the double bond at one end of where the double bond used to be. And so remember when we're talking about radicals, I made the point that why would anyone care about putting Cl or Br on an organic molecule? It's because this gives us a chemical handle that we can do more chemistry with. So this reaction is similar. It puts halide on a molecule, but this time the starting molecule was an alkene rather than an alkane, which is what it's always going to be in most of those radical reactions. Okay, so before we talk about the mechanism of this reaction, let's talk about thermodynamics. Are these reactions favorable, and how do we know? Well, we can do a simple-minded bond energy calculation, just like we did with the radicals. And here, remember that the delta H standard of the reaction is equal to the bond energies of the bonds broken minus the bond dissociation energies of the bonds that are formed. Now, when we talked about bond dissociation energies in the context of radicals, I said that these bond dissociation energies are measured for the homolytic bond breaking, the radicals. We're not talking about radicals anymore. Why is this reaction, why does this equation work here now for a reaction that's not a radical reaction? Why are we using numbers that pertain to radicals? And that is because way back in Gen Chem, maybe you remember the concept of a state function. Delta H is a state function, and a state function is a function whose value depends only on the initial state and the final state of the system, and not on how the system got to the final state from the initial state. Remember that? Remember state functions? So this equation where we're calculating a delta H is good when we're talking about radicals, or where we're not talking about radicals, because delta H is a state function. It doesn't matter whether the reaction is radical or not. The value of delta H only depends on the initial state and the final state. The initial state is the reactants, the final state are the products. Okay, so if we look at hydrohalogenation, or using HCl, just as an example, we're trying to calculate whether these reactions are thermodynamically favorable or not. The double bond gets knocked out, and Cl adds to one end of where the double bond used to be, and H adds to the other end of where the double bond used to be. And now what I'm going to do over here is make a little reckoning here of the bonds that are broken. Okay, so what are the bonds that were broken? Well, one of the bonds that was broken was a carbon-carbon pi bond. The carbon-carbon sigma in this double bond, remember how double bond is a pi bond and a sigma bond? The carbon-carbon pi bond was broken. The carbon-carbon sigma bond, nothing happened to that. So this carbon-carbon pi was broken, and that's worth 267 kilojoules per mole. Another bond that was broken here is the HCl bond, and that's worth 412 kilojoules per mole. The bonds that are formed, well, a carbon chlorine sigma bond was formed. That's a new bond. This carbon chlorine sigma bond was formed, and that's worth 328 kilojoules per mole. And another bond that was formed here that wasn't there before was this carbon hydrogen sigma bond, and that's worth 413 kilojoules per mole. Okay, so now I'm ready to calculate the delta H of this reaction. Delta H standard will be the bonds that were broken. That's 267 plus 412 minus the bonds that were formed. That's 328 plus 413. And so this works out to be minus 62 kilojoules per mole. So is the reaction favorable? Oh my heavens, yes. You're going downhill in energy. Delta H is exothermic. The system is giving up heat to the surroundings. It's losing 62 kilojoules per mole. The initial state is up here. It's going down 62 kilojoules per mole. That is very favorable. And if we do calculations like this for HF and HBr and HI and all of this other stuff, we come up with the very same conclusion that these reactions are all thermodynamically favorable. We're going to get a pretty good yield of product. Okay, going to talk about the mechanism, but before we can talk about the mechanism, let's do some product prediction, right? Because we don't need to know the mechanism in order to come up with the product in many cases. All right, so what would be the product that would be formed here? Draw the structure of the product. So what happens when an alkene reacts with a hydrogen halide like HCl? The carbon-carbon double bond is degraded to a single bond, and H adds to one end of where the double bond used to be, and Cl adds to the other end of where the double bond used to be. So the product here is going to be that double bond got taken down to a single bond, and Cl added to one end of where the double bond used to be. Yes, I could have put the Cl up here. It's the same thing. So how'd that go? Yes? All right, so let's try another product prediction. HBr, draw the structure of the product. Notice no peroxides. Well, so this could be a crisis here because I see 4 double bonds. Which one is going to get the Br? Which one is going to get the H? Which double bond is going to be knocked out? And which double bond is going to have Br added to one end of where the double bond used to be and H to the other end of where the double bond used to be? Well, it looks like a crisis, but it really isn't, because benzene is not an alkene, right? If I had written out this problem using the Amit-Robinson formulation of benzene, then you probably wouldn't have had a crisis, right? Benzene is not an alkene. Benzene is represented as cyclohexatriene for historical reasons, right? So if I had given you this very same problem using this other way of writing benzene, there would have been no question of which double bond would react, because you're only looking at one of them. So it's important to keep in mind that in this family of reactions we're going to talk about are not reactions of a benzene ring, because benzene is not an alkene. Benzene is an arene. Right, so the double bond that reacts is this double bond in the four-membered ring. Okay, so now let's talk about mechanism of the reaction. Okay, so we have the alkene. That's a nucleophile. It's electron rich. It has an electron pair, in this case a shared pair, that is available for bond formation. And we just talked about how the H end of the HX molecule is an electrophile. So nucleophile gets together with electrophile, right? Most of chemistry is just this: something that has a lot of electrons chasing something that doesn't have as many electrons. Negative charge chasing positive charge. And so the first step of this reaction mechanism is that the electrons in this pi bond reach out and grab the proton from HX, right? This is the nucleophile chasing the electrophile. I'm showing the movement of electron pairs, of the electron pair using that double-headed arrow, not those annoying fishhook arrows that we see with radicals. And now hydrogen cannot be bonded to two things at once. Hydrogen either forms 0 bonds or 1 bond, so that when the nucleophile attacks this proton, this HX bonds has to snap, and it's going to snap in the direction of the more electronegative halogen. Okay, so what I've written here, this is something that's crucial for you to understand how the convention of using these curved arrows. These curved arrows do not represent the motion of atoms. They represent the motion of electrons. Just like when we're writing a resonance structure, those arrows represent the motion of electrons, not the motion of atoms. Okay, we can draw the transition state for this reaction. That carbon-carbon single bond, nothing is happening to it. But now this pi bond is going away, so I'm going to illustrate that with those dotted dots as a dotted bond. And meanwhile, those electrons have moved in the direction to pick up that proton from HX. Meanwhile, the HX bond is going away. And so I'm representing that with those with that dotted bond, and not quite finished here yet with this transition state, because we'll see in the next structure that this X is neutral, but it's just gained an electron pair. So at the transition state, this has a partial negative charge. This carbon down here has a partial positive charge, because it's going to pop out positive in the next structure that we draw. At the transition state, positive charges are developing, negative charges are developing. So this is what our transition state looks like. Okay, so next, that double bond has snapped. It's been degraded to a single bond. The hydrogen has added to one end of where the double bond used to be, and X minus is now this free swimming entity, and this positive charge, this partial positive charge, has consolidated to a full positive charge. This is a carbocation. It's a carbon that has only a sextet of valence electrons that has this positive charge. Okay, so now what we see here is we have a nucleophile, X minus, and we have an electrophile, the C plus. Most of chemistry is just nucleophiles chasing electrophiles. Something has a lot of electron density chasing something that doesn't have as much electron density. So the next event here is going to be the attack of this nucleophile on the electrophile. And once again, I'm using these curved arrows to show the motion of electrons, not the motion of atoms. Okay, so nucleophile attacks electrophile. I can draw the transition state for this step where that X is about to form a bond to the carbon. That the negative, this arrow shows I'm pushing electrons away from something that's neutral, that's negative. So in the transition state, that X has a partial negative charge. That negative charge is going away. And this arrow shows that this positive charge on this carbocation is in the process of disappearing. So this carbocation, or that carbon atom, has a partial positive charge at the transition state. Okay, at the end of the reaction is that partial charge has a partial bond has consolidated, whoops, should be an X, could be BR, but I'm going with X. That partial, looks messy. That partial bond has consolidated to a full bond. The negative charge on the X has gone away, and the positive charge on the C has gone away, and the atoms of HX have added across where the double bond used to be. Okay, so that's the mechanism of this reaction. And this is a whole lot to say about this. Okay, so first up is, let me just emphasize the use of these curved arrows. These curved arrows represent the motion of electrons and not the motion of nuclei or of atoms. Okay, so incorrect use of curved arrows. And if you draw the arrow ass backwards, if it should be going this way, but you write it the other way, that's points off on the final exam. I'm going to take points off for that. So let's get how to use these curved arrows correctly. They represent the motion of electrons, not the motion of atoms. So if I look at this guy here and react him with HX, the product of that first step is going to look like that. Okay, so now let me show you how to use these arrows wrong. Well, it looks like the H went here. But there I'm showing the motion of an atom. These arrows represent the motion of electrons, and H doesn't have any electrons. Yes, I know that it looks like the H went from HX to that carbon, right? But this is not how we use curved arrows. So that is totally wrong. And I'm warning you, I'm threatening you. that if you draw these arrows going in the wrong direction, that's points off on the final exam, right? These arrows have to be showing the motion of electrons. Okay, so that's the first thing to say about this reaction. Another thing to say about this reaction mechanism, right? Remember, this is a transition state. Remember, this is a transition state. Bonds are being formed and bonds are being broken. And so this mechanism has two steps. This is step one, leading to this carbocation. And then this is step two. And these transition states, we're about to draw an energy diagram for this reaction. These transition states, those are the hills and everything else that lives in a valley. Okay, so the energy diagram for this reaction is going to have, the mechanism has two steps, so it's going to have two hills. It has two transition states. It's going to have two hills. So in the energy diagram, the energy diagram has as many hills as it has steps, or another way of looking at it, as many hills as it has transition states. So this reaction, this energy diagram that we're about to draw has two hills, but those hills are not of equal height because one of these steps is slow and the other step is fast. Tell me in the chat, which is the slow step and which is the fast step, right? This is step one, leading to here. Here's step two, leading to here. One of these steps is slow, the other one is fast. Which is which? Tell me which is the slow step, step one or step two. Tell me in the chat. Step one or step two. Which one is slow and which one is fast? Which one is the slow step? Anyone want to give it a shot there in the chat? Two steps, one is slow. Okay, I see a one, but you're not telling me whether that's the slow step or the fast step. So tell me which is the slow step. Tell me what's the fast step. Don't just tell me step one. Anyone giving it a shot? Okay, well, I see every possibility that could be, so that's good. Okay, so step one, this is the slow step. Step two, this is the fast step. Okay, and now how can we understand that? Well, in the first step, we're asking molecules that have octets. We're asking a molecule where everything has an octet to lose an octet when it becomes this carbocation. Atoms want to have an octet. This carbocation doesn't have an octet, it only has a sextet. So I'm asking stuff that is happy to become stuff that is unhappy. That is a slow step. Okay, step two, something that doesn't have an octet is recapturing its octet. In step two, it's going to be very fast because I'm just making everything happy again. So step one is slow, step two is fast. All right, so how can we visualize all of that on an energy diagram? All right, so the energy diagram is going to have, this is going to be energy, right? And energy comes out in various flavors. It could be a delta H, it could be a delta G, it could be, if you remember Gen Chem, it could be a delta U or whatever it is. That's just the energy of the reaction. And the reaction mechanism has two steps. It's going to have two transition states. The transition states live on hills. It's going to have two hills. Okay, so initially, these are our reactants over here. We have the alkene, and we have HX. And the first step is going to be slow. That means a big hill leading to something that is high in energy, leading to that carbocation, which is very high in energy because it doesn't have an octet. So I'm going to place the carbocation up here. And I'm going to make a big hill. See how big that hill is? Oh, that's a slow step because the system has to have enough energy to overcome this energy barrier. And who lives up here on this hill? That's transition state 1. I'm not going to draw it. Okay, then step 2 is we're going to be going to form the final products. Well, when we started talking about this reaction, we talked about the thermodynamics of this reaction, and we saw that the overall reaction is thermodynamically favorable, so that the valley where the products live is lower than the valley where the reactants live. The overall energy change is going to be negative. So our products live down here in a valley that is lower in energy than the starting material. And now if we look at the Hammond postulate, right, we see that this is downhill in energy, so this is going to be a tiny little hill. This is going to be a tiny little hill like this. Okay, so there's our energy diagram for hydrohalogenation. The first step is slow. It has this big system, is living down here. It has to overcome all of this energy barrier to reach that carbocation. But the second step is very, very fast. That's a tiny hill. Okay, so that's how we can express the rate phenomenon using this energy diagram. We need to talk a lot about the carbocation intermediate because this is an intermediate that we haven't talked about before. We're just meeting him maybe for the first time, has a sextet, a carbocation. This has a carbon that has only a sextet of valence electrons. The carbocationic carbon, just like the pi-accepting radical carbon, is sp2 hybridized and planar. The sp2 hybridization state has an unhybridized p orbital. When we were talking about pi-accepting radicals, there was a dot living in this orbital. But here, with a carbocation, only has a sextet of valence electrons, so this orbital is totally empty. There's no electron in there. Okay, so the carbocation is planar, and it also has an empty p orbital, right? So this is an empty p orbital on that carbocationic carbon. Carbocations also have an order of stability, which is exactly the same as the order of stability that we encountered for radicals, and for the very same reason, sigma donation, right? The most stable carbocations will be the resonance stabilized carbocations. And these are more stable than tertiary carbocations, which are more stable than secondary, which are more stable than primary, which are more stable than 0 degree or methyl. These are the least stable carbocations. And for the very same reason. reason. Sigma donation. Right? The additional alkyl groups donate electrons to that empty p orbital, reducing its electron deficiency, and that's what stabilizes it. Resonance is much better at that than sigma donation, so that the enhancement, resonance, so the enhancement is greater. Okay, so this is, so the carbocation looks, is very similar to a radical, except that it has an empty p orbit. Okay, so let's do some problems. I'm going to write out some carbocations here. I want you to rank them. One is the most stable carbocation. Okay, so that's a little pyramid with a positive charge here. Then we have that one. And then this one. And then that one. Okay, so tell me in the chat, who's number one? Who's the most stable carbocation? Is it the one on the left, the one on the right, one of the ones in the middle? Tell me in the chat, who's the most stable carbocation? The first one, the second one, the third one, or the fourth one? Okay, somebody give it a shot here. Even if it's a wrong answer, I'll tell you if you're wrong. Who's the most stable carbocation? The first one is the most stable. The pyramid is the most stable. Okay, most popular wrong answer. See, the most popular wrong answer is that the most stable one is this one. Far right is the most stable one. This one is the least stable. Why is that? Okay, so I told you who the least stable one is. Now you tell me, why is that the least stable one? Huge deviation from planarity. The carbocationic carbon is sp2 hybridized and planar. So look at this pyramid. I mean, I don't care if it's tertiary, but this carbocation has to be, or wants to be, or best is when it's planar, right? Is that planar? Oh my heavens, no, if you sat on it, it would hurt, right? So this is the least stable carbocation because it has a huge deviation from its ideal geometry. The ideal geometry of the sp2 hybridization state is 120 degrees, and it's planar. This guy's nowhere near any of that. This guy, he's the most stable because what is the interior angle of a hexagon? It's 120 degrees. And plus, this guy the carbocationic carbon can be planar. The interior angle here is 60. That's far from 120. The interior angle here is 90. That's a little bit closer. So our ranking in order of stability would be that. Okay, so what we're looking at here is the geometry of the carbocation. It wants to be planar. It wants to be 120 degree bond angle. Okay, let's try another ranking problem. So this one's easier. Okay, so same business, rank in order of stability. Tell me in the chat, who is the most stable carbocation? Or tell me who the least stable one is. Well, okay, so finding the least stable one, that's easy, right? It's not a trick question like the one we just did. Who's the least stable? Anybody out there? Okay, the least stable one is going to be this one. Least stable is going to be this one. Why? It's primary. All of the other ones are secondary, right? So secondary carbocations are more stable than primary carbocations. Yes? Yes. Okay, so now of the remaining three, tell me in the chat, who's the most stable of the remaining three? Who's number one? Yeah, it's going to be this one. This one is the most stable one. And then the remaining ranking would be, this one is going to be 2, and this one is going to be 3. Okay, so what are we looking at here? Well, we're looking at primary is worse. We're looking at secondary, that's secondary, that's secondary, that's secondary, is worse than, is better than primary. So that's, that decides who gets the gold, the silver, and the bronze. But the reason that a carbocation is unstable in the first place is because the carbocationic carbon is electron deficient. It's missing electrons. Anything that is going to increase its electron deficiency is going to make it even more unstable. Fluorine is a highly electronegative atom. Fluorine is sucking electrons away from other atoms. The reason the carbocation is unstable in the first place is because it's electron deficient. Fluorine is, the fluorine that is present in these molecules is making that carbocation even more electron deficient than this one, which doesn't have a fluorine sucking electrons away. And the effect is attenuated by distance. If the electron withdrawing atom is closer to the carbocation, it's going to be sucking more electron density away. So here, the fluorine is far away from the carbocation. Here, the fluorine is closer to the carbocation. And so that explains the rest of the stability order. Okay, so time for another trick question. Okay, but I already let the cat out of the bag, so this is not really a trick question. who's the more stable carbocation? Okay, I'm expecting 100% accuracy here in the chat, right? This is a trick question. Who's the more stable carbocation? The one on the left or the one on the right? No, no one wants to give it a shot. The more stable carbocation is, well, okay, so I see every possibility here. What if I told you this was a trick question? Would that help? Maybe not. Who's the more stable? Okay, so now you're equal, no. This guy here is more stable. Well, now why is that? Can somebody tell me in the chat? Why is this one more stable? The fluorine, I just talked about how if you put an electron withdrawing atom close to the carbocation, that's going to destabilize it. Here I've put the electron withdrawing fluorine as close as possible to the carbocation, yet it's more stable. Why is that? Anybody have a guess? Oh, resonance, exactly. Right, because this guy here has a resonance, is a resonance stabilized carbocation, whereas the other carbocation is not. Right, so this fluorine isn't donating any electrons here, so this is not resonance stabilized but this one is. So we can't forget that about resonance stabilization. Okay, we have time for more ranking problems. All right, so let's just give a pair here. This guy versus this one. Okay, and once again, tell me in the chat, who's the more stable? The guy on the left or the guy on the right? Which one is more stable, left or right? More stable, guy on the left. All right, so why is this? So this guy has a resonance structure. This guy has a resonance structure, looks very similar. But this one has a third resonance structure. More resonance structures usually translates into greater stability. The electrons have a bigger box to run around in, and that stabilizes the carbocation. More resonance, more stabilization. Okay, so time has elapsed.